All right, so in this example, we're actually going to be given one of these statements written in symbolic logic, and we're going to try to convert this thing to a nice English sentence. Once we have this as an English sentence, we can start to chat a little bit about whether or not this statement is true or false. In this case, it's actually going to be false, and we're going to use this notion that this thing is false to help springboard our conversation into actually trying to represent the negations of these different types of quantified statements. So in this case, like I mentioned, it is written in symbolic form. You can see all of these horrible little symbols all coming into play. There are the two really big chunks of this thing. The portion on the right is going to be this sentence or this predicate that is going to describe something about this expression x squared plus 1. In this case, I'm claiming that x squared plus 1 is going to be even. On the other side is going to be talking about where those x's coming from. In this case, these x's are going to happen to be these nice little integers. You can see that really big, fancy, handsome z in there that's going to represent this set of all possible integers. And then the very last portion of this is going to be this notion of what type of quantifier am I actually dealing with. In this case, you can see that there's that universal quantifier, this weird upside down a, which is going to say I'm going to have to test against every possible integer. This is this idea of this huge loop that's going to cycle through all possible integers. What's going to happen is that once I grab one of those integers, I'm going to have to constantly test, is x squared plus 1 going to be even? Okay, so let's go ahead and see if I can actually write this thing down as an English sentence. I'm going to start with this quantified portion out in front. That's usually the easiest part to work with. In this case, I'm going to say something about for every or for all, something to really indicate that I'm using this universal quantifier. In this case, let's just say for all. So for all integers, x. Okay, that's exactly what that front circled part is saying. For all integers x, or for all x that happen to be integers, or however you feel like phrasing that thing. What I'm going to put at the end then is exactly this little sentence. This x squared plus 1 is even. All right, so it's not so bad actually converting these things kind of back and forth. Going from a sentence to symbolic form is sometimes more challenging because there are all the different ways that you can actually represent these things, and you have to kind of dig out what somebody's trying to actually represent. But going from the symbolic form to an English phrase, you just kind of go with the very vanilla version of this. Is just for all integers x, blah. In this case, for all integers x, I'm claiming that x squared plus 1 happens to be even. All right, so now let's think a little bit about whether or not this thing is going to be true or false. Sometimes the false one is actually the easier thing to answer. In general, trying to show something is false is, all you got to do is just find a counterexample. So let's look at a few just test examples. Let's choose maybe our favorite integer. In this case, let's say 1. 1 is a very nice integer. Okay, what happens if I take 1 and square it and then add 1? Well, 1 squared is 1, and 1 plus 1 is 2, and that's even. So that works. Yay. That's not enough though, obviously. Just testing one single thing is hardly ever going to be enough to test anything. So in this case, let's try one more. Let's go up one notch. Let's say 2. Well, if I take 2, if I square it and add 1, I'm going to get 2 squared, which is 4, and 4 plus 1 is 5, and you can see that that thing is odd, so this is actually false. All right, so let's try to phrase this a little bit more bizarrely of kind of describing why this thing was false. The idea for the falsehood of this statement is because I could find one integer, at least one integer, that broke this final conclusion of this thing. So the idea is why false? Well, the idea is that there exists an integer, x. In this case, that x happens to be 2, such that x squared plus 1 is odd. Oh, excuse me. All right, so that's exactly the kind of breakdown that's happening in this case. But also what happens to be very, very nice for that is that that portion in red that I just wrote down, this kind of description on why it's false, actually ends up becoming the negation of my overall statement. So if this is my statement that I'm initially dealing with, I'm going to have for all x and z. I'm actually going to use this kind of predicate notation to say this is the fact of something being even, in this case e of my x squared plus 1. Well, if I'm looking to negate that thing, what's going to happen is that it's just going to pick up that exact statement that I saw up above. The idea is that there's going to exist some x that happens to be an integer, and what's going to happen is that the opposite value of that's going to occur. In this case, it's going to be the negation. And if I don't like saying not even, I can actually just represent that as odd. So there exists some integer, such that that expression is odd. And the fact of that is a very nice result that comes into play in this world of quantifiers, is that it's very, very easy to negate these things. This little kind of equivalence that I just represented is actually something that occurs over and over and over again.